Hi everyone, this Diophantine equation is an important and mainstream subject in number theory, and I'd like to use this Pythagorean triples and twist of the Pythagorean triples to introduce this Diophantine equation and toward to something more called the rational solution of these equations, and where I introduce several different methods of looking at this problem. And this is a vast area, so I can't really, and I don't know everything about it, but I'd like to introduce at least just a little bit, which is the standard, but still is always interesting to introduce these interesting ideas. And the problem itself, it's intrigued me at the beginning, and I always thought that it's worth laying down all of them together. So here's a right triangle, and Pythagorean theorem states that a squared plus b squared equal to c squared. And it is a very important theorem. It's a most fundamental beginning of a part of the all sorts of geometry. And also it leads to the discovery of irrational numbers such as the square root of 2 and so on. So you can easily put down whole number or rational numbers that we understand over here. That hypotenuse easily escapes the realm of the number we understood back then. So it's also introduced, used as introduction to something called irrational number. More correctly, the point is that we want to think about this nice triangle with this sides all being integers. So that's the subject in here. If you're looking at an equation like this and three unknowns, we can call three variables, and we're looking for the solutions to the three variables satisfying this equation in integers. So we call this integer solutions. So that's the subject. We're looking at Diophantine equation. It means an equation in polynomial equations. You're looking for integer solutions. So probably this triple called 3, 4, 5 triangle is most well known, Pythagorean triples. So I sketched them over here in the 3, 4, 5. And there are many ways to approach this problem. Mainly we want to find all the solutions in here, and here's an example. And I will pretend, or maybe someone will discover by just searching more and more integer solutions to this equation, they notice that there's always one that is right next to each other, that meaning that, and 4 and 5 just consecutive integers. So maybe we can start with that. Can we always find integer, three integers that fit into this right triangle, and two of them are right next to each other? I think this question really leads you to the full solution. So I think it's a good starting and good pretend starting. And if you really look at the data, or go and discover more triangles with integer sides, right triangle with integer side, and that's pretty reasonable motivation to go for this relationship and figure out there are three numbers that fit into this triangle and satisfying that relationship, this one apart. So I think we're going to start. I'm going to write as y here, and that one will be z, and is y plus 1. Since it's unknown, I'll better use just x, y, z. So that's what we're looking for. Is there's this x and y and z, where z is simplified in here as a y plus 1. Can we find these numbers such that this Pythagorean theorem is satisfied? So I'm going to write down that equation in here. Here it is, x and y, and z has more structure now. It's one bigger than the one side we're looking at, one in here. So because it's a square and that's a square, and that square term cancels, it leads you to a linear. So that's the, before we go into any details, the focusing on this linearity showing up, it allows us to solve easily in terms of integer solution. Go and expand it yourself and try to simplify. So when you expand this part, and this is a binomial theorem, and y plus 1 squared becomes like this, and when you cancel y squared, you end up in here. Okay, so here's one thing that you can interpret. If you start with putting the y in there and try to, if you try to put arbitrary y in there and try to figure out what kind of x satisfy that will be actually more difficult than, right, why don't I vary x in there? I can put any x in there and try to satisfy the right-hand side condition. That's a lot easier if you actually try both of them. So if x can be free, if I put anything in there, can I kind of match the right-hand side? I don't know if somebody noticed if it is linear, it's always going to be in that shape, but just for this problem, it's simply an odd number. Any odd number will be expressed in this way. So right and left-hand side is a squaring business in here. So if you square odd number, then you will always end up at odd number. So we have pretty much good freedom. As long as I keep this odd property in the left-hand side, I can put anything in there, and the right-hand side is going to match this odd property. All right? When we generalize this idea, this type of thing still holds if you use the congruence relation here. So I'm going to come over here to this side and make x really free variable. And we just talked about any odd number is expressed like this. And anytime an integer y and go through it like this, or whatever the variable is here, this is going to be always an odd number. So in that observation, we claim that if x is odd number, like 2, let's say here's 2, we'll call it k in here, 2k plus 1, any odd number is expressed like this, and this is always an odd number if and only is condition. Then, because this side is odd, and if you square it, that's going to be in that form odd number. So I'm going to actually go and square it and match with 2y plus 1. And this is another good spot, and you wanted to actually do this one yourself. So here it is. If you square x, it looks like this. You can see this is even part and plus 1, so you can easily match this one with a 2y plus 1. So if x is any of this form, k being freely any number, can there be always y that matches to that? You simply solve this equation, and that's and here is y. So here it is. 1 and 1 cancels. If you divide both sides by 2, this is y again. From there, we have z, solution for z. Z is simply 1 bigger than y. Therefore, we have 2k squared plus k plus 1, and that is the z value. So if you plug in any k value in here, then this will fit into this Pythagorean triples. Sorry about the mistake. I missed that coefficient 2 in front of it, so I insert it there. And next I'm going to show I use the Sage to generate some of the few examples, some of them you're familiar with. I'm sure this is going to recover our 3, 4, 5 example, and then it's going to show more of them. So here's some of the few examples where k equals 1 in here. If you plug in k equals 1, you recover this 3, 4, 5 triangle. When k is 2, you go to the next odd number and recover this new triangle, 5, 12, 13, and they're 1 apart from each other. That's very nice. And third one, this corresponds to k parameter equals 3. So if you plug it in here, you get 7. So 24 and 25 next to each other when this k equals 4, and these 40 and 41 is right next to each other. And as you plug in more numbers, you will get in more and more Pythagorean triples, such that these two sides are just 1 apart from each other. So this idea actually extends to, what if it is a 2 apart from each other? What if it is a 3 apart from each other? Things like that. So that's the next situation we're going to go through. So you may try this example with, what if it is a 2 apart and 3 apart yourself? And that's really good exercise. And hopefully from that experience, you can generate this, generalize this idea to arbitrary number like n apart from each other. So that we're going to go through that calculation. It's really fun. It's good, more reasonable approach than just clean, polished, efficient proof that is usually introduced in the book. So I thought it's more fun to do it this way. So if you like, and go ahead and try 2 apart and 3 apart examples. And I'm just gonna, the rest of the part is going to be quite a repeat, so I'm not going to go through all this calculation again, but I'm just going to show you quickly explain if there's anything that is different from here. So go ahead and try difference 2 and difference 3.